uh, at NERC. I work on all things IPR, and really glad to be here today in front of you. Let me bring that up and share my screen. Right, I think I need to share the other screen. 1 second.
Yeah, looks good. Thanks.
Okay, cool. Yeah, today I'd like to talk about the grid forming functional specifications that NERC IPS has published sometime like last year, and also go over some of the motivations behind those. All right. Have you ever been to a party where the party rules are not very clear, whether you should bring food or drinks or anything at all, or just show up? So I guess I should say before I start, what I'll be presenting today, aside from the facts in the published paper, are my own personal opinions and not necessarily that of NERC. Having said that, the traditional generators, like synchronous generators, have been bringing their own system strength to the party, right? You will see that the IBRs, the grid forming IBRs don't, and since you're joining here, you will probably already have an idea what the grid forming inverters are, and they have the potential to do that, right? So, but if only this topic is as clear as something that you can see and eat, and it's only so much the party, so long the party can go on without food, right? If you only bring drinks, we can only last for so long before we all run out of energy and keep going. So that's the kind of the analogy that I like to give to the generator resources bringing the system strength, along with the energy that they provide. So some quick background. Back in 2021, NERC IPS wrote a white paper on grid forming technology. One of the recommendations was that the IPS should further develop the standardized processes, practices, and requirements, as well as a test procedure to support the rapid adoption of GFM technology moving forward. One of the obstacles that we identified in that paper was establishing clear interconnection requirements regarding the expected performance, testing, and validation of the technology. So in simple terms, how do we ask for grid forming, and how do we know what we got is grid forming? That's what we set out to do in the white paper published in September 2023. It functionally and purposefully qualitatively define GFM capability, and also provide methods to verify such capabilities by test simulations using OEM provided EMT models. As part of that, of course, we cover some model quality fundamentals. We provided a test system, test setups, and success criteria. GFM technologies has been commercially available for battery energy storage systems, either standalone and as hybrid. We know there's a very small incremental project cost if everything else being the same, and all new BESS should really be designed and commissioned and operated with the GFM mode. There are some additional grid stabilizing characteristics that we laid out in the paper. Of course, just because GFM doesn't mean it can connect automatically without any studies. It's just like any other plants, it requires interconnection studies, system impact studies, and also requires testing against the spec, right? So what we find it in this paper is a functional spec and tested against it. Due to the nature of the controls, the response time frame, it requires EMT studies to properly vet for whether the submitting device meets the functional specs. And we'll go through all of that one by one. Now, what's the motivation for looking at grid forming technology in battery energy storage systems? Excuse me, I forgot one S in there. Well, if you look at here, we've got 430 gigawatt of solar with hybrid, and you have standalone 300 gigawatt of batteries. But if you only look at the batteries that are part of the other IBRs, so there's 312 standalone and another 357 gigawatt of storage as part of the hybrid plants. So that's a lot of capacity that is coming up online, and we want to get ahead of the game and start preparing the industry in terms of having the necessary specifications to ask for. So if we wait, the cost would be that we end up with all these sites that could have been grid forming and could have been helping the strength of the system. Now, why GFM invest today? Well, they're cost effective. The easy step towards the BPS reliable stability and a very high IBR penetrations. Grid forming characteristics, grid stabilizing characteristics are that they have, right? And also, all of that is in the software, right? Just like IBRs, it's a software-defined device, and such GFM is no different. It's in the software. And particularly in the BESS, in the battery energy storage systems, there's already a store energy on the DC BESS that provides a huge energy buffer to be able to carry out some of the grid stabilization response. We know that they are already available in BESS inverters today, and there's a growing experience with the grid forming technology and the success stories. And so already, anyway, the existing need for much more BESS. We've already seen the previous slide. However, there's a significant cost of inaction if we kind of just sit and admire the problem. So although it's retrofit is possible, but it could mean additional hardware costs or additional complexity could be a large roadblocks. So, just a caveat to make here is that, I say all in the software, unless additional capabilities are desired or needed. For example, it could be higher overload current or greater HVRT write-through capability, for example. So they could mean a different hardware, and then those are not necessarily in just the software anymore. Now let's look at an overview of the functional spec for BESS, right? So we can compare and contrast what we have on grid forming and grid following. So capability-wise, we can go down from the top. We're talking about subcycle voltage and frequency support. Now the subcycle is a keyword here. If without that quantifier, if we just say voltage and frequency support, people will just say, well, we already have that, right? But no, those are dynamic, more of a quasi-steady state response. But here we're talking about subcycle response. Resistance to phase jump, and system stress support, right? So those are the three main grid stabilization characteristics that we're looking for when we define the functional specs for battery energy storage systems. Now, the other ones are, for example, the ability to operate with lossless loss synchronous machine. Grid forming can do that. Grid following maybe, if you can perfectly match the load and generation, or sometimes accidentally you could have a resonance conditions that you can temporarily sustain an island. So that's why the star is there. And of course, the grid-forming inverter should also be able to perform the other functions that grid following already do: dispatchability, steady state voltage control, dynamic reactive power support, effective power frequency control, disturbance right through performance. We wouldn't expect the same, if not better, right through performance from the grid forming. Fault current and negative sequence current contribution. Now again here, as we all know, inverters are current limited. However, how that current is injected in the subcycle time frame is what makes the difference here. And of course, last but not least is cyber and physical security. So, and in the next slide, we'll go a little bit more into the details for the first three attributes. So what do we mean by the subcycle voltage and frequency support? Right. So that's something that is specific to GFM. In our spec, we call out and we define it as GFM shall provide autonomous, near instantaneous frequency and voltage support by maintaining a nearly constant internal voltage phasor in a sub-transient time frame. So that's how we put it out in the spec. The second, the resistance to phase jump. GFM should resist near instantaneous voltage magnitude and phase angle changes by providing appropriate level of active and reactive power / current output in the sub-transient time frame. So I said / current because obviously, you can't really have power in the sub-transient time frame, but you get the point. Now, if we do those two things that we mentioned, we are supporting system strength, right? So grid forming shall reduce the sensitivity of voltage change for a given change in current in the sub-transient time scale. So it's how stiff your voltage is. So it should help to locally stiffen up the voltage in around its location, right? So that's the idea. And for the third point, the ability to stably operate with loss of last synchronous machine. The GFM should be able to stably operate through and following the disconnection of the last synchronous machine in its portion of the power grid. Obviously, this is merely used as a sort of a defining test. Obviously, we're not going to be isolating the actual power grid in this fashion. But however, if a device can do that, it provides all the grid stabilization characteristics that we're looking for, the benefits with the reliability of the BPS. Well, with the specs, now the transmission owners, planners, planning coordinators can leverage and those specs that we publish and establish those as requirements today, now, right? So we've answered the industry call where, well, how do we ask for it? Well, here's how we can ask for it. And TPs and PCs can also leverage the recommended set of tests that we provided in this paper to test new project models to ensure that they meet the GFM specifications. Whilst we talked about how to ask for it, in essence, what, in the remainder of the slides, we'll look at how, meaning how to verify that it's a GFM. And what we proposed in the paper is a simulation test, and we particularly leveraged the electromagnetic transient simulation tools to perform these tests. Well, I should acknowledge that there are different opinions on qualifying an interconnecting resource as a GFM, right? So what you could say that's precisely the purpose of the UNIFI consortium itself, right? It's one of the purpose. So here we are, we are provided a version of it. the version that we provided, we wanted to use a method that is simple to implement and it's agnostic to the control topologies. We don't get into details like there's a Droop control, a VSE, a virtual machine control. We don't care what the underlying technology is or control topology is. As long as it can pass these tests, we are going to call it as a qualified as a grid forming inverter. But first and foremost, before we actually do model-based assessment, we want to establish and touch on the model quality fundamentals first. We want to be using the OEM provided validated models and validation test reports that shows a benchmarking between the EMT model response with the either hardware in the loop or container test response. They should be pretty much on top of each other. And ideally, you'll be looking at not only RMS quantity, but also looking at the sine waves and look at how the sine waves matches up in the first half a cycle and a cycle. So that's the level of details you can expect from these validation reports. And of course, attestations on model matching the S-build configurations and settings from inverter OEMs, as well as from the plant level controller OEM. For some technologies, there could be slower quantities that could be communicated between the inverter and the plant level controllers to sort of absorb some kind of control response from one control level to the next level. Right. So in those setup, the plant level control validation is also quite important. For more information on this model quality fundamentals, I will refer you to the inert reliability guideline on EMT models and simulations that we published last year, March 2023. We cover in there model quality checks, what kind of documentations to ask for. So please have a look. All right, now the fun stuff. The GFN functional test system. So it's a simple one BESS system, and it's purposely designed to be simple. Please keep that in mind, right? Because again, we are trying to qualify things, and obviously there's more tests that one can perform, and you are encouraged to do that. But the subject matter experts that pull together to write the paper, this is a collective wisdom that these tests is sufficient to do the job. So first of all, you can see there's a synchronous generator. It's about 3 times the project BESS. Then you have a project battery energy storage system, and there's a duplicate of that model, which will be half rated. And then there's a load, and the load will be matching the BESS. And we'll discuss why we think. Yeah, I think I should actually discuss that here in this slide. You know, obviously the test is going to be going to involve, you can guess it, taking out that synchronous generator and leaving the battery, 2 battery systems in an islanded situation with the load. And what we'll be looking for is, did it survive that disconnection, and did it maintain the stability afterwards, right? So that would be our test. Now the idea behind the duplicate BESS is that we can see how if they're using some kind of a Droop controls, so how they play against each other, right? It's kind of hard to put another one that's from another OEM, because you're looking at this particular interconnection, so you very likely only have that OEM, and so it just makes the test a lot easier to just use the same model. It tests 2 things, right? One is control stability, sharing the power between the 2, and the second is the modeling. Right? Can the model support multiple instances of the same type? And our recommendations here would be that you ask the GO or the developers to provide you both those models. From my experience going through some of these tests, so we actually tested these tests that we put in here ourselves, And through the experience, we learned that it actually is it's quite challenging to take a model and change the settings to make it a half-rated project. There are different OEMs have different settings at different places you have to change. So it's best to just ask the developer who provides you the model, can you please give me the project specific one and make a copy of that, but make it a half-rated. Everything else the same. So some of the conditions, the MVA of the two battery combined should be greater than the load. Well, that is to make sure that we have the current and power adequacy to actually support the load. We're not testing that perspective. We're testing the more of a transient nature. The MVA of the synchronous generator should be greater than the megawatt charging of the BESS and the MVA of the load. So in one of the tests is where we do the test with the battery put in charging condition. So the synchronous generator should be large enough to provide the charging load and the load as well, the charging of the battery and the load as well. The Q mode, the reactive control mode of the battery should be in voltage control, and both batteries, BESS 1, BESS 2, should employ the same voltage and frequency droop settings and set points. So everything else is the same. Only the difference is the MVA rating of those two. The tests that we're going to see next are intended to subject the GFM battery to extreme frequency, voltage, and phase jump events, way beyond what they could normally see when they're on grid forming on the BPS. Nonetheless, this is supposed to test the functionality, so that's by design. Okay. I just realized I've been looking at the wrong screen, so I think let me go back here. All right, so I've been talking to this slide, but I have that. Let me see here. No, actually, that's the right slide. Never mind. Okay. So we've seen the test system, the GF. Now we're going to talk about the test themselves. Well, the GF and BESS and the test must pass all these tests to qualify, all three tests to qualify as a GFM. One or two tests, right? So it will be pretty hard for purposely tuned grid following inverters to pass all three tests. Especially the test 2 is fairly hard to pass. So this is to address some concerns that what if you tune the grid following to be to pass this test, right? So that's a really concern. Well, it's got to pass all three tests, and it's got to pass all three tests with the control settings that is supposed to be utilized on grid, right? So those settings might make the grid following pass some of the tests, but those settings, if you use them on the on-grid operation among the other generators, can lead to instability. So one of the requirements is that the settings in here, the control settings, right, gains and things like that, are actually using the what the project would use when it goes on grid. So test 1 is the battery initially discharging. After disconnection, it ends at a higher level of discharging. It assesses the best performance following the generator trip, 1 operating within their limits and in discharging state. Test 2 is testing the same thing, but when the generator is in charging state, it actually have to transition from charging to discharging state, right? The current needs to flip 180 degrees, phase jump to be able to support that. So that's a fairly rigorous test. And test 3 is actually testing them close, either at or close to their operating limits, where the performance is tested at the maximum active power, the site limit. Of course, there are many more tests one can do, right? You can do this and then followed by fault, and see if if you rise through the fault and things of that nature. But we're keeping these to a minimum, yet effective set of tests, balancing the complexity and the effectiveness. Now, there's some important notes. I covered that. Although these require the BESS to be operated in the absence of any synchronous generation, many GFM battery will never be operated that way. They will be on grid. Regardless, the ability to survive these tests indicates the controls have the necessary properties that we expect from the grid forming in a grid connected conditions, the grid stabilization attributes. These tests are not, of course, substitute for interconnection studies. This is just to verify that it's grid forming, and you still got to do the interconnection studies, just like any other plants. And of course, these tests do not guarantee that the facility will be stable for a specific location on the grid. Interconnection studies, as always, are critical for ensuring the reliable operation of the BPS for each specific interconnection resource. So that still needs to go through that. Now, if setting changes happen during the interconnection studies, these steps should be repeated with the new settings. Now we talk about the test system. We talk about the test. Let's talk about the setup. How do we set up and how do we determine it's a successful grid forming behavior? So first is initial dispatch. Thing that there are 3 tests that, in the interest of time for this presentation, we're only going to look at the worst case one, the test 2. So in this one, we will dispatch the battery, the project battery, at half of its maximum charge power limit, and the duplicate one, the half-rated duplicate one, will also be dispatched at half of its maximum charge power limit. So they're both charging in the beginning. The test sequence involved is run this until the system is stable. So you see the power flow conditions are as you expect, and there's no oscillations. And once you achieve steady state, trip the synchronous generator. You will see that the success criteria that we're going to lay out are intentionally designed to avoid being overly prescriptive, right? So we're leaving room for engineering judgment, but at the same time, sufficient enough to make the call. So success criteria, pre-trip. Before we trip, we want to check these off, right? 1 second here. Yeah. Give me just 1 second. All right. Sorry about that. So first, the BESS output matches what we set it to, the dispatch power level. The second, the synchronous generator active power output matches the rest of the load, and plus the battery charging levels. The frequency should be at 1 per unit. The voltage at BESS 1, well, that's only one BESS, should be within the 5% of nominal. So we want to make sure that we're within the normal operating conditions, right? So that's essentially what we're trying to do. Phase voltage, current waveform should not be distorted. There should not be oscillations in RMS quantities. The reactive power output from all devices are within limits, right? So it's steady state. We're not pushing any limits. We're well within limits, in fact. And once we check all those spots, then we will trip the synchronous generator. Now, success criteria for post-trip. Immediately following the trip, the BESS output should be well controlled, meaning the current's not going crazy, things like that. The system frequency and voltage should not oscillate excessively or deviate from the steady state level for any significant amount of time. You will see the example results. And so here we were careful with the language to stay away from being prescriptive, like, it should settle within a certain number of seconds and things like that, right? So now we leave in those freedom for engineering judgment and for control tunings and innovation in the controls, right? But very high level, these are what we're looking for. Second, the voltage set us to a stable operating point. The final voltage is as expected based on the droop and deadband settings. Frequency settles to the stable operating point. Again, this final value should be based on the droop and deadband settings. Any oscillations should be settled. Any distortion observed in the phase quantity should dissipate over time. You may see some distortion in the current waveform initially, in the first 1 cycle or so, but that should dissipate over time and become more sinusoidal. Active power from each battery should move immediately to meet the load requirement and settle according to the frequency droop setting. And same for the reactive power. Now, we'll be looking at both RMS quantities, like RMS voltage, as well as power, active and reactive power measurement. So, of course, the response time of the power measurements depends on how much filtering you put on the meter model, right? So you got to take those into account. So that's why we're going to look at both RMS and instantaneous waveforms. So this is what test tool looks like in the EMT tool. You've got on the top, you got the battery, laser pointer. That's your project battery. This is your half-rated duplicate battery here, connected to the same BESS. You have the synchronous generator. So this example, we're using 100 megawatt, right? And the load is here. And so this breaker is stripped at a predetermined time, right? So you will run into steady state first and see when it reaches steady state, and then you will run it again. But this is the second time with the breaker programmed to trip after the steady state. I think one thing that I would like to note is the load. We want to have the load, some reactive components in the load as well. We wanted to have at least, or I should say at most, 0.95 power factor, right? So when I say, like, so if it's 0.95 is the most, then you want to test it at 0.9, 0.92, for example, or even 0.85, right? So again, just keep in mind to balance the reactive capability of the assets you're testing with the load. But nonetheless, we want some reactive component in the load. Now let's look at the sample results. This was tested using one of the OEM EMT model that's equipment specific, that has actually been deployed in real life in several projects. So this is not coming out of the lab or anything like that. So this is product. And you can see on the top is the RMS voltage of the BESS. And the second is the frequency. And the third is, we got 4 traces here. The blue is the power of the synchronous generator, active power. The green is the active power of the load. I guess the red is the active power of the battery. And the purple is the active power of the battery, the duplicate battery, the smaller one. Same for the reactive power down here. And last is the RMS current of those same 4 devices. So some points to make here. So you can see the frequency drop right away, and then it catches it at some reasonable value. You can see that. You can ignore those frequency spikes, right? That actually depends on how the frequency is measured. are calculated by the simulation tool, right? So obviously, if you look, well, you'll see that when we go to the instantaneous quantity, there's a phase angle change in the voltage, so that it's going to throw off any frequency measurement logic and create spikes. So these are artificial spikes, and don't concern yourself with those, but just kind of watch for where it catches it. And you can see it catches it and then immediately slow down the root off and leading to the steady state. So this is kind of what we mean by well controlled. You can see the current. The current is not oscillating or anything like that. So that's what we mean by well controlled. Any oscillations damped out, right? So you can see there's a little bit of overshoot and undershoot in the Q. Again, it's just kind of one cycle, whatever the frequency of the oscillation is, better damped out fairly quickly. So these are the example of what we mean well controlled and in reasonable manner. Looking at the point 2 here, you can see the active power from the battery, the 2 batteries jammed pretty much instantaneously. Instantaneously in the context of RMS quantity, of course, right? And you can see that change to match the load. So load power merely dropped. Now, of course, you can zoom it in and you can see there's some ramp, but that's the artifact of the power measurement, right? You can measure power subcycle. Same thing for the reactive power as well. You can see the jump pretty much fairly quickly. It jumps up. What's more obvious is in the current, right? The RMS current. So here we're plotting about 20-second post trip. So this depends on you want to see that it's settling, and so however long it takes, you want to wait and make sure that it actually doesn't start growing again, right? So here, although I'm showing 40 seconds, you actually want to run as long as you stay seeing the oscillations and make sure that it doesn't blow up, say 60 seconds later, right? Now in the instantaneous quantities, same test. You can see the phase angle change in the BESS voltage, right? And you can see this second one is the instantaneous current from the synchronous generator, right? So the breakers are programmed or simulated to close on zero crossing, so they would not cut off the current, so they will actually open at zero crossing. So that's what you're seeing here, and whenever it actually opens, you will see a bump in the voltage. You can see a small slight change in the phase angle of the load current, right? And so what we really want to focus here is 2 things. Number 2, look at the magnitude of the battery current. So it was around 0.3 kiloamps, and post transient is 0.4. So it jumps within half a cycle, right? So that's the magnitude. And you can also look at the phase shift, right? So it doesn't continue in the same phase and then slowly change the phase angle, the magnitude. It actually changes the phase right away. So those are the things you want to look out for, look for in terms of the characteristics. We actually tested these test procedures with 2 different OEM models, and we see similar responses from both of them. And same thing for the BESS 2 as well. So both the speed, the current magnitude increases, and the current phase angle changes. The injected current phase angle. So what are the key takeaways from this and recommendations? Well, the GFM technology is commercially available. It's field proven for transmission connect applications, particularly for BESS. There are a couple of pilot projects that is you're probably aware of. It's under UNIFI that's going to be field trying this in the United States. But this has been field proven anywhere else, right? Well, shouldn't say anywhere else in major markets like Australia, Hawaii, Europe. All new interconnecting BPS connected battery should be designed, carefully studied, and commissioned with the GFM controls enabled. That's our recommendation. We know that it's available. Why not ask for it? TOs, TPs, and PC should leverage the IRPS grid forming white paper that I presented today to begin the process of establishing GFM functional specifications. So what this means is you should expect to see the TPs and PCs, the utilities and ISOs beginning to adopt these specifications and the requirements. EMT modeling enables verifying the crystallization characteristics of the BESS. The resources are available from IRPS as well as EMT task force that I coordinate. The white paper provides functional specs and simulation tests. The guideline on EMT modeling provides guidance with getting good quality models. And the task force is working on numerous guidance materials. You might be interested to know that one of them is a curated repository of EMT modeling resources, kind of like an EMT curriculum. And a new guideline on when to perform what types of EMT studies and how to do it. Let me see here. So I think I can skip this one. Maybe let's see. Well, in September 2, we published a disturbance report. It's California. It was a 2022 in California. There was an event, and several battery energy storage systems were involved. Same story as what we've been publishing of the previous disturbance reports, right? You may have heard of Odessa 1, Odessa 2 reports, right? But here, though, it's a different resource type. Here we're seeing this similar risk with the battery energy storage systems. So I just want to kind of balance the expectations, right? So we've talked about, the growing share, the growing injections of battery systems into the BPS, which is good news. Which also implies we will have a reliance on those batteries in the future, and if we're gonna rely on them, we want them to actually perform fairly well. We want them to ride through normally clear faults, and we are seeing the first signs that they're exhibiting the same problem with the PV plants. So, battery supposed to help the other IBRs resources, other intermittent resources, but if something that we're gonna rely on itself is not reliable, then we'll be in trouble. So it's just to kind of balance that thought for us, that reforming, great. At the same time, there are basic things that we need to get right to make sure the settings are good, and they're commissioned properly, the data are good, it's modeled properly, the plants right through properly, and the right through capability is assessed adequately and before commercial operations. So these are basic things that we want, not just batteries, but all IBR plants all generated plants to be able to perform. Then on top of that is the grid format that we discussed today. So with that, we can go into Q&A.
Thank you, Aung. This was very interesting. Thanks. So we do have a few questions in the chat box. So I'll read names and then I invite the persons to ask their question if there are